So up until this point, we have talked about the difference quotient, and then we looked graphically at the slope of a tangent line. And then we finally put it all together and said, hey, this thing is called a derivative, and we can just use the difference quotient to find the slope of any tangent line for that graph. But there's got to be a better way, right? This is pretty labor intensive if we wanted to find the slope for a point on a graph. So can you decide what the shortcut is here? So what we have here are two columns. In the first column, you have just your original function. In the second column is your derivative after using the difference quotient. And I apologize, that got cut off a little bit there. What I want you to do is take a minute and look at the two functions. Look at, for example, f of x here and the derivative of f of x here. And see if you can start finding what a shortcut might be. Is there an easier way to come up with the derivative? If I were to give you the function, could you just tell me what the derivative is without having to actually go through that entire difference quotient? So I want you to pause the video here, take a few minutes, look at the two columns and see if you can come up with something that will allow you to go a little bit quicker to that derivative. So hopefully you were able to start to see some patterns emerging. If we look at any function that is a linear, actually I'm going to start with any function that doesn't have a variable in it at all. Whoops, sorry about that. I meant to use a highlighter. So, wrong highlighter. If I look at all of these functions where I just see a constant term, we get f of x, or f prime of x is just 0. Well, then when I start looking at my linear functions, so these are all linear functions, right? They're just x to the first power. When I look at those ones, look at those derivatives, right? So in each of those, for f of x equals 2x plus 1, the derivative just ended up being whatever was right in front of our x term. Same thing with f of x equals negative 3x plus 4. Derivative just ended up being whatever was in front of the x term. Same thing again with our constant function, or with our linear function. And then if there was a linear function, or sorry, if there was just a value, it was like saying, oh, plus 0 there, right? So this plus 4 just was like saying plus 0, so they didn't write it. This 5 was like saying plus 0, and that goes back to these ones. A constant function just has a derivative of 0. A linear function just had the derivative of whatever the coefficient of that x term was. Okay, let's keep this going. So if we kick it up a notch and we look at a quadratic, oops, sorry about that, we have x squared minus 4x. Okay, let's take a look at that derivative. And then here's another quadratic, another derivative of that. Here's another quadratic. Here's another derivative for a quadratic. In the quadratic, hopefully what you're noticing is, okay, so the linear term still was there with its coefficient, right? The linear term's coefficient still showed up. If there was a constant term, it was still like saying plus 0. Our quadratics, though, went from x squared to 2x. So a couple things happened there. We now have a coefficient and the power is smaller. Here we went from negative 2x squared to negative 4x. And here we went from negative 3x squared to negative 6x. So each of our x squareds became one power less. Hopefully you're starting to see the pattern here, and I missed a linear function here, but the same kind of rule applied. So the shortcut is this, and I'll kind of talk you through this last function that we see in our table. Our shortcut is this. Whatever we see as the exponent, okay, so that 3, we are going to multiply it by whatever the coefficient of that term is. So 3 times 5 gives us the 15. And then whatever this exponent is, it decreases by 1. So instead of being 3, it's now 2. So let's do that here. We take the power, multiply it by the coefficient. That gives us plus 4. And then we decrease this minus 1. I'll just write a minus 1 there. So that became 4x to the first power. Here, that same thing happened. That's x to the first power. If we multiply x to the first power times negative 3, we get negative 3. And then if I subtract 1 from that, we get 0. And that's why it's x to the 0, which is the same thing as saying 1. And then this just we would say the exponent on x is 0, so 0 times 4 is just 0, right? So we end up with that plus 0 at the end, which we don't need to write. So that's our shortcut. So what I would like you to do is try to find the derivative of this f of x here. Pause the video, see if you can find it, come back and check your answer. Okay, let's see how you did. So to figure this out, I'm going to take the 3 as the exponent on x cubed, multiply it by -2. So I get -6x, and then I subtract 1 from that exponent. So it's -6x squared. Then I'm going to take the 2, multiply it by -7. I get -14x, and then I subtract 1 from 2, and I get x to the first. So we'll just write x. Then I'll have, this is a 1 multiplied by 6 plus 6. Subtract 1 from that 1, it's just x to the 0 power, which I don't need to write, that's just 1. And then anytime we see a constant, that has a derivative of 0. So if you wanted to say plus 0 at the end, you could, but you could also just write it like this. Now, when we start talking about some of the, sorry about that, more kind of interesting ways of writing x, we have something like the square root of x. So we want to talk about how we can write the square root using exponents. And that's really f of x equals x to the 1/2 power. Now I'm going to take a second here and go down to the next example and talk about how we can write 1 over x with an exponent. And that would be f of x equals 1 over x, that'll be x to the -1 power. And this all goes back to your exponent rules. So let me talk for a second about the last example. If I want to find the derivative of that, I'm going to take this -1 and I'm going to multiply it by the 1 in front of the x. So the derivative of f of x would be -1 times x, and then I have to subtract 1 from my exponent. So that ends up giving me an exponent of -2. Now, while this is correct, I'd like to rewrite this in a slightly different way because I don't like having powers that are negative. So just like we rewrote 1 over x as x to the -1 power, I can write x to the -2 power as 1 over x squared. And instead of being 1 over, I have the -1 as a multiplier there. So this would be my derivative. Now let's take that and go back up to the previous example. So I'm going to take that 1/2 and multiply it by the coefficient of x, which is just 1. So for the derivative of f of x here, I'm going to get 1/2 x, and then I subtract 1. So that gives me -3/2. Now, just like I saw a moment ago, I'd like to rewrite this so that I don't have any negative exponents. So I can think of this as 1/2 times 1 over x to the +3/2 power. Now let me rewrite this. Multiplying those together, go up here. F prime of x would be 1 over 2 times x to the 3/2 power. Now, I kind of like that. It's a little bit better, but honestly, I don't like fractional exponents either. So a fractional exponent just means we're dealing with some kind of a root. And remember, it's the denominator of your fraction that determines the root. So I would have 1 over 2 times the square root of x, and then that 3 would become the power of x. This would be our final result. Now, like I said, this is not wrong. We just like the simplification, the rewrite, a little bit nicer. All right, there's a lot of these on here. I just want to give you a handful to try, okay? So I'd like you to try just at kind of picking a few here for you to try just to start to get some comfort from this. I'd like you to try maybe just 1 and 3. So go ahead and pause the video, try 1 and 3, and come back and check your answers. All right, pay attention to how you did. Make yourself a note if you missed any and you can't figure out why you missed them, and we can talk about those in class. let me have you try a couple more. So this time, I'm going to have you try some that have a radical involved in some way. Okay, so let's do 8 and 9. Go ahead and pause the video and come back and check your answer when you're finished. All right, on 8, very much like what we did in the problem on the other side of the paper here, except we have a 3 as a coefficient. So what that does is it just changes our value in the numerator. So instead of being a 1, we'll see it be a 3. On 9, it's a little tricky because there's a power of 1 on x here. So when we multiply the 1 times the coefficient of our x, which is radical 3, we get 1 times radical 3 is radical 3, and then we'll subtract 1 from x, and 1 from the power on x, and we get 0. So this one's a little tricky. It's actually a linear function. It's just written kind of funny. All right, let's try a couple more. So this time, I'd like you to try 5 and 10. Go ahead and pause the video, come back and check your answer when you're finished. Okay, how'd you do? So once again, 5 is a lot like what we did on the front of the paper. The difference is your coefficient is 2 instead of 1. So that just changes what's in your numerator. And then 10 seemed a little harder than it was maybe. X to the 4th, if you wanted to think about this term, you could also think of it as 1/4 times x to the 4th. Take that power, multiply it by the 1/4, you get 1, and then subtract 1 from 4, and you get 3. So you get 1 times x cubed. And then the rest of this is like what we did on some of the other ones. Okay, couple more I'm going to have you try here. Just to mix it up a little bit, let's do number 6. Sorry about that, meant to highlight. There we go. So let me highlight here. This one, number 6. Let's try number 12. And how about number 14? Let's do those 3. So 6, 12, and 14. Go ahead and once again pause the video, come back and check your answer when you're finished. Okay, so number 6, as I showed you up above here, we can see how we could rewrite 4 over x squared as 4 times x to the negative 2 power. And then we can rewrite x squared over 4 as 1/4 x squared. And then from there use our rule. 12 seemed a little tricky, but e squared, e is not x. When we're finding the derivative, we're only finding the derivative with respect to x. E is just a number. If you don't remember what that is, you can go ahead and type e to the first power into your calculator and you're just going to get a number. So when we say e squared, we're just talking about some random constant term. So when we find our derivative, the derivative of a constant term is just 0. And then finally here, there's a couple ways you could have done this. You could have started by subtracting everything here and then finding the derivative. I just found the derivative of each thing and then did the subtraction. So either way, you should be able to get 3 minus 2x. Okay, I think that's it. Actually, let's do just 3 more. Let's do 23, 24, and 27. So go ahead and pause the video, try those 3, come back and check your answer. Okay, so the last couple here, 23 is pretty straightforward, just a larger power on x, no big deal, same process. 24, again, it's very similar to one of the examples we did on the front of the page. When you have an x in the denominator, you can rewrite it with a negative power, and then you go through your process and you end up with what I have there. And then finally 27, the square root of 7 is just a constant. So when we find the derivative of a constant, that is just 0. If you're up for a challenge, you're welcome to try a couple of these towards the bottom here. 28 is a good one for a challenge, 29 also a good one, and 30. And then if you are curious about what the answers to those are, you can ask me and I will give those to you in class. Okay, have a great day. I will see you in class.